Hello and welcome back into our channel. We're looking at probability and we're going to specifically do a video on questions and answers on probability and set theory. If you've been following our videos carefully, you've noticed that we've been doing our lectures in a 1 minute short videos, 1 minute short videos, and we've been able to complete the probability and set theory lectures. And we're going to be able to focus on this video. It's going to be long, but it's going to cover questions and answers strictly on probability and set theory. So without much wasting time, join me and let's zoom straight right in. So we're going to imagine that the first question we're going to have here, we are being told that there's a number that is chosen at random. A number is chosen at random. That's the beauty of probability. A number can be chosen at random, and the number is from 5 to 25. 5 to 25, and it's inclusive. It is inclusive. What it means is that 5 could be picked, 25 is also part of it. Numbers that you can choose at random is from 5 to 25. 5 being inclusive, 25 is also part. Now we're being told to we're going to find the probability. We are going to find the probability. I'm going to find the probability that the number that we are going to choose at random, the probability that the number that is chosen is a multiple of 3. Find the probability that the chosen number is 1, is a multiple of 3. Is a multiple of 3, and 2 is rather a multiple of 5. Do you remember our formula on probability of event? Probability of an event, don't forget that formula. It's very, very, very important. It's a critical formula. Now, probability of an event is given by the number of that event. You can count the number of that. So the event that you're looking for, the number of the items in that event, divided by the number of everything. That number of everything is what we call the sample space. It's called the sample space. It's called the sample space. Now, what the event we are looking for is that the probability that is a multiple of 3, which means we need a number of multiple of 3 divided by the number of everything, the number of everything. Now, the first thing we're going to look for is the multiples of 3 in this question, or the everything, the sample space, or what we call the everything. What is that everything or sample space? Now, pretty much that is from 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So this is a sample of everything. And if we count the number of things in it, that's giving us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So the number of everything here. So the number of everything here, we have 21 of it. Now, the next thing we can be looking out for is the multiple of 3. So when we say multiple of 3, if we want to focus on the sample space, how many items are in this sample space or everything that are multiples of 3. Now, multiples of 3 are when you're adding 3's together. So the first thing is going to be 3. The next one is going to be a 6. When you add another 3, get 9. You add another 3, get 12. But in the sample space, 3 is not here. But the second one, which is 6, is here. So 6 is there. The next one is 9. 9 is also there. The next one is 12. The next is 15. The next is 18. The next is 21. The next is 24. And it ends there, according to the sample space. All right. Now, we can see that the number of the multiple of 3 here, is 1, 2, 3, 4, 5, 6, 7. There are 7 items there. So now we can be able to complete our work, where we have the probability of the multiple of 3, the probability of multiple of 3, which is going to be the number of the multiple of 3 divided by the number of everything. will be our final answer. Now we're going to have is going to be the numerator. The number of multiple of 3 is here. It's 7. We put 7 in the numerator, and then in the denominator we have the number of everything. The number of everything is 21. When we cancel out, we get 1 over 3, and you can see that 1 over 3 is the same as 0.333, and we know one of the axioms of probability is that probability can never be less than it can never be less than 0. That means it can never be a negative number. It can also not be more than 1, or it shouldn't be greater than 1. It shouldn't be greater than 1. So this answer satisfies that particular concept. That we are saying that the probability of an event should always lie within 0 and 1. It should always lie between 0 and 1 over 3 is 0.33. It satisfies this particular condition. Now let's go take a look at the second problem. The second problem, we're told to look for the multiples, probability of the multiples of 5. For the multiple of 5, we can see that that is going to be the number of the multiple of 5, number of multiple of 5 divided by the number of everything, number of everything, number of everything. Now, the multiple of 5, let's look for the multiple of 5. Now, how do we get a multiple of 5? So we keep adding 5s, we keep adding 5s. We keep adding 5. Now, the first number is 5 because 5 is in the sample space. If you remember, 8 is also there. Sorry, not 8, 10. 10 is there because we have to add. We need to add 5s to get a multiple. So the next is 10. 10 is there. The next is 15 is there. Then it's 20, and then the last one is 25, which is there. Now, we can be able to tell that the numbers 1, 2, 3, 4, 5. So the number of the multiple of 5 is what? 1, 2, 3, 4, 5. There are 5 items there. The next thing we're going to look for is the number of everything, which we've already discovered, which is the items. There's 21. Therefore, the probability of the multiple of 5 is given as the formula, which says the number of the multiple of 5 divided by the number of everything. The number of everything. Now, if that's the case, the number of the multiples of 5 is 5 divided by the number of everything is 21. It's 21, and that gives us our answer. You know, there's a fraction. It also satisfies the condition that the probability of any event should lie between 0 and 1. That gives us a hint that at least we've done the right thing. I think at least we've done the right thing. Now let's look at another question here. Let's look at another different question here. Now remember, a question is saying that a number, we still have a number. There is a number, and that number is also chosen at random. It's chosen at random. And where are we choosing that? It's chosen at random from a certain set. It's chosen from a set S, and that set S is given as 4, 7, 10, 13, 16, and 19. So this set is already given to us. We don't have to go and look for it. Now, the question is saying that what is the probability that a chosen number is an even number? What is the probability that its chosen number is an even number? Now, the probability that it's an even number should be the number of that even numbers, right? The even numbers, the number of even numbers divided by the number of everything, Now, the number of everything, like we did say, is the same as the number of the sample space. Please do not forget that. The number of everything is the number of the sample space. So we can tell is 1, 2, 3, 4, 5, 6. There are 6 items in the sample space. Now, the next thing we can look for is the number of even numbers found within the sample space. And we can tell that the number of even numbers, before we look for the number, before we look for the number of even numbers, let's look for the even numbers. What are the even numbers from the sample space? That's what we need to list first. The even numbers from the sample space, 4 is one of them. And what's an even number? It's a number when you divide by 2. There's no remainder. You get a whole number. There's no remainder. So 4 is satisfied. 4 is such a number. You divide 2 by we take 4 and divide it by 2. You get 2. It's a whole number. No remainder is left. But if we take 7, we divide 7 by 2, we're going to get a 3 because 2 times 3 is 6. And that's the one that is very close to 7. But there's going to be a remainder of 1. So 7 cannot satisfy that. So 7 is not part, but 4 is one of them. 10 is. 10 is an even number. 10 is an even. 13 is not. 16 is an even number. And 19 is not. 19 is not. Now, the number of even numbers found here, the number of even numbers found here is 3. There are 3 of them. Therefore, we can now complete our work. Therefore, the probability that a chosen number is an even number, the probability that a chosen number is an even number, is the number of even numbers found. The number of even numbers found. Then divided by the number of everything. The number of everything. Now, the number of even numbers we've discussed is 3. So we put our 3 there. We divide by the number of everything that we've also discussed as 6. When we cancel out, we're going to get 1 here, and it's also going to go here 2. So basically have a half. Half is the same as 0.5, and we can tell that this also satisfies the condition or the axiom of probability that a probability of an event should always lie between 0. It should always lie between 0 and 1. 0 and 1. 0 and 1. So I hope so far you are appreciating the formula for finding the probability of an event. It'll come to you as handy. Let it be handy. Let it come to you as handy because you need it. You did it. If so far you're not getting it, please pause the video. Take a little break, come back, feel refreshed, and start all over again. And you'll see that everything will be coming to you so fast and so quickly. Now let's take another problem. We're going to take a complete different problem. Now we are seeing that this problem says that in a class there's a certain class, and in this class we have 20 boys. There are 20 boys. The boys are 20, and the girls are 35. The girls are 35. Now the question says, what is the probability? What is the probability that when you select a student randomly, what is the probability that when you select a student randomly, it's a boy? The probability of a boy. What is that? What is that? Now, the formula says that probability of a boy is the number of boys divided by the number of everything. So I know we are selecting a boy. It shouldn't be 1, right? Because we know that those boys, you can pick any of them, so it can't be just 1. The number of boys that are there, which is 20, the possible number of boys that are there is 20. So to pick a boy randomly could be any of them. So the number of boys there is going to be 20 instead of just 1, right? So now, but before we go ahead, let's look at the number of boys. All right, let's look at the number of boys. So the number of boys has been given to us to be 20, and then we also have the number of girls also given to us as 35. So the number of everything, which is which we said is a number of the sample space. The number of the sample space is the same as the boys plus the number of boys plus the number of girls. That's the number of everything. And then we end up getting 20 plus 35, which gives us 55. All right, it gives us 55. So 55 becomes everything. And the boys is also 20. Now, the formula says that the question says we should look for the probability that when we select a student randomly, we will get what? A boy. So the probability of a boy, we said, is the number of boys divided by number of everything. I think that's what we arrived at. So the answer is going to be the number of boys is 20. We divide it by everything, which is 55. And then we try to reduce it from there. Now, 5 can go into 20 4 times. 5 will go into 55 11 times. So our final answer is 4 by 11. And we can tell that this 4 by 11 is less than 1. It's not up to 1 because it's a fraction. And that satisfies the condition that the probability of any event lies between 0 and 1. It lies between 0 and 1. It lies between 0 and 1. Now let's look at a completely different problem, which is completely different. Now here, we are going to be looking at something called the fair coin. A fair coin meaning that the coin is not biased, it's fair. it means it's a regular coin that we all know. That makes it fair. If it's not regular, it's not a regular coin. Then it's not fair. It's a biased coin. So every coin that we pick, there's always going to be a head side. There's going to be a side called the head, and then there's also going to be a certain section called the tail. So if you find a coin that only has a head and a head on both sides of the coin, then it's an unfair coin. It's a very, very biased coin. It's a very, very biased coin. But in this problem, the question says there's a fair coin, meaning that one side is head and the other side is a tail. But this time around, we are tossing this fair coin. We're tossing it twice. We're tossing this fair coin twice. Now, the question says, what is the probability? What is the probability of obtaining exactly two heads? Probability of obtaining exactly two heads. So when we toss it twice, what is the probability that the heads are going to show up two times? They're going to show up two. That's exactly what he's saying. Exactly two heads. Now remember, we said that in probability in one of our lecture videos. We did state that anytime we toss a coin, there are two outcomes. So there's a formula. We said that is the number. If we want to know the number of the total outcome, number of total outcomes. If we want to know, how do we know? It's a formula. We are saying that it will be the number of outcomes per a toss. So each toss, just one toss. When we toss it only once, what is the possible outcome that we're going to get? It's only two outcomes. When we toss a coin, it's only two outcomes. It cannot be three outcomes. It cannot be four. It cannot be five. It's only two outcomes. And those two outcomes, it could be a head or a tail. That makes it two outcomes. Just like the probability of a human being is either the human being is dead or the human being is alive. Only two outcomes. So if we toss a coin, a fair coin, if we toss it once, the number of outcomes, it could be a head or tail. So there are two outcomes, and then you also take to the power of the number of trials. The number of trials is the same as the number of experiment, or the number of tosses, or the number of trials, or the number of experiment. Now in this question here, we know that the number of outcome per toss is two times because it's either a head or a tail. And then the question says we toss it twice. So we take to the power of 2, and that gives us 2 times 2, which gives us 4. It gives us 4. Right here, we have 4. Right here, which is our total outcomes. Now, how do we list this? It's easy. We're going to have the first toss. The first toss could show up as either a head. The second toss could also be a head. The other possible outcome is that the first toss could have been a head, but the second one will show up as a tail. Yes. Or the first toss could have been a tail, and then the second toss could have also been a tail. Or the first toss could have been a tail, and the second toss would have been a head. These are the total outcomes, and you can see it's 1, 2, 3, 4, as the formula has given us right here. So now we know that this is our sample space. So we know that our sample space, I'm going to write it maybe here. We know that our sample space is what we've indicated: head, tail, tail, or a tail and a head. This is our sample space, meaning that the number of our sample space, or the number of everything, is 4. We know that number. Now, the question here says that we should find the probability. We're going to find the probability that exactly 2 heads show up. So the probability of exactly 2 heads, we're going to get a number. Don't forget, it's the number of exactly 2 heads. And we divide it by the number of everything. Now, if we look at this sample space that we've found here, if we look at this, exactly 2 heads is only occurring once. A head and a head. It's only one. So that means that the number of exactly 2 heads is 1. So in the formula, we have 1 at the top divided by the number of everything, which is 4. And then we end up getting 0.25, which kind of sums up our answer, and it falls within the condition that the probability of any event should be between zero. It should be between 0 and 1. It should be between zero. It should be between zero and 1. Now, let's imagine with the same problem, we're asking that what's the probability that there's no head? There is no head. What's the probability of no head? Is the number of no head divided by the number of everything. Now, what is the number of no head? You can be able to tell from the sample space. No head is only this one here. Can you see that? This one here is the only option. It's only one. It occurs only once in the sample space, right here. No head, right here. No head. So it's only one. The number is only one, and the number of everything is 4, and that gives us 0.25 as well. Now, what if it says we should look for the probability of at least one head. The probability of at least one head is the number of at least one head divided by the number of everything. Divided by the number of everything. Now, the number of at least one head, it means that it could be one head or more. One head or more. And right here, this is one of it. Tail and a head is right there. This one, there's no head here, so it's not part. There's a head, at least one head here, and there's also another head. It's about 3 of them. There are 3. The number of at least one head is 3, divided by everything, which is 4. And then the answer is 0.75. All right, I hope this helps. I hope this problem clarifies. It clarifies a lot of things. I hope it clarifies a lot of things. Now we're going to be looking at something different, a different question, a different problem set. We are still going to be looking at a fair coin. We have a fair coin situation, but this time we are tossing it 4 times. We're tossing it 4 solid times. We're tossing it 4 times, and then we are being asked to find the probability of obtaining at least one head. At least one head. Now, from that formula, we know that the probability of at least one head, if we want to look for this answer, it is the number of at least one head, and we divide it by the number of everything. Number of everything. So let's look for everything first. We need to know what the everything is. The everything, because we are tossing it 4 times, we can create a table. We can create a table where we have maybe 2 tosses. 2 tosses where you have a head, tail, tail, and tail and a head. We also have another 2 tosses here. So we also have another head, tail, tail, and tail, head right here. Now we can be able to list the outcome. So this, if we take this and this, it's going to be 4 heads. Can you see that? If we take this and that, it's 3 heads. But if we take this and this, we have 2 heads and 2 tails. Also, the last one here is going to be 2 heads, 1 tail, and a head. This and this gives us head, tail, head. This and this gives us head, tail, tail. This gives us head, tail, tail. This gives us head, tail, head. This and this gives us tail, head. This gives us tail, head, and tail. This gives us tail, tail. This gives us tail, tail, and head. This gives us tail and head. This gives us tail and head, tail. This gives us tail and head, tail. And the last one is going to be a tail and a head, and a tail and a head. So this is the probability of everything. If we count that, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we can say that the number of everything is 16 of them. But what about the number of at least one head? So it could be 1 head, it could be 2, it could be 3, it could be 4. Yeah, that's what we're looking for. So if that's the case, we can see that here there's more than 1 head here. So this is one of it. This one to more than one head. This one is two heads here. This is also three, so we need it. This is also possible. That, this here, there's at least one head. There's one head over here. There's no head here, so we leave it. This one, there's one head, one head, one head, one head, and one head. So that's about 15 of them, if you remember, if you can see, except this one here, except this one right here. This one is not part of it. So therefore, we can be able to solve our problem. We can be able to find answer to our problem. So the probability of finding at least one head, at least one head. What they said is a number of at least one head, divided by number of everything, the number of everything. And we know the numerator is going to be number of at least one head is 15. Divided by number of everything is 16. 15 divided by 16. And that gives us our final answer. And it also satisfies the condition that it lies between 0 and 1. 0 and 1. I hope this helps. Now let's look at maybe one last problem for this video. And then we can bring the video to an end. Let's look at one last problem, and then we can bring our video maybe to a conclusion. Now let's look at this time, instead of looking at a fair coin, we are going to be looking at a fair die. A fair die. So we're looking at fair dice, a fair die, right? We're looking at fair dice, and then there are two dice, right? There are two dice, two of them, two dice. All right, we have two dice. We can say die A. You can name them die A, and a die B. Now they are fair because if you take any regular die, it has one. It has the numbers. It has the numbers 1, 2, 3, 4, 5, and 6. So die B also has to have the same thing because there are two fair dice, 4, 5, and 6. If it doesn't show that, then it's an unfair die or it's a biased die. So this problem, we are having two fair dice, A and B, and each of them are numbered, the faces are numbered 1 to 6, and they are being thrown together. They are thrown together. The dice are thrown together. They are thrown together. They are thrown together. Two dice are thrown, two fair dice are thrown together. So what we do is that we can construct a table and say that this is our die A. This column here can be die A, and then this could be die B. So pretty much we have maybe 1, 2, 3, 4, 5, and 6. And you also have 1, 2, 3, 4, 5, and 6. Now, it means that if we take these two pairs, it's going to be 1 and 1. Here it's going to be 1 and 2. This and this is 1 and 3. That and that is 1 and 4. This and this is 1 and 5. In that order, 1 and 6. Here, this and this is 2 and 1. This and that is 2 and 2. 2 and 3. 2 and 4. 2 and 5. 2 and 6. This one and that will be 3 and 1. This and this will be 3 and 2. This will be 3 and 3. 3 and 4. 3 and 5. 3 and 6. Here is going to be 4 and 1. This and this is 4 and 1. The same 4 in this 2 gives us 4 and 2. 4 and 3 gives us 4 and 3. 4 and 4. 4 and 5. 4 and 6. Here it gives us 5 and 1. 5 and 2. 5, 3. 5, 4. 5, 5. 5, 6. The last one, 6 and this gives us 6 and 1. 6 and 2. 6 and 3. 6 and 4. 6 and 5. 6 and 6. In that particular order. Now, what's the question? The question says we should find the probability that the two dice show the same scores. The two dice, we should find the probability that they show the same scores. When you throw them together, the numbers that appear on each of them is the same scores. What's the probability of the same score? So the answer is going to be the number of same scores. We need to look for the number of same scores and divided by the number of everything. The number of everything. Yes, the number of everything. Now, what is everything? That's what we have done. This is our everything table. That's what we have done. So what's the number in there? What's the number of everything? What's the number of everything? What's the number of everything? The number of everything in here, we can count it. It's 1, 2, 3, 4, 5, 6. And then on this link, we have 1, 2, 3, 4, 5, 6. So 6 times 6 will give us 36. So there are 36 of items in there. I mean, this is 6, this 6, this 6. We count them, 6, 6, 6. And that gives you 36. Now, what is the number of same scores, or what is the same scores in this everything table. The same scores, we can tell this is the same score. That is also one of it. This, and that. They are showing the same thing. Now, the same scores is 1, 2, 3, 4, 5, 6. There are 6 of them. Now, finally, our answer is going to be probability of same scores. So, probability of same scores is the number of same scores, as we have indicated, same scores, divided by number of everything, right? We've stated that. Now, the numerator same score is going to be 6 divided by everything, which is 36. And then we end up getting 6 over 36, which is goes here 1, equals here 6. And our answer is 1 over 6, which satisfies the condition. Now, what about if we are told that, or we are asked a question that, what is the probability that when you sum them up, you will get more than 10. Probability that when you sum them up, when you sum them up, you get more than 10. With the probability that when you sum them up, you get more than 10. More than 10. So it's a formula. We're still going to be using that same formula, but probability that the sum is more than 10. Now it's going to be the number of sum more than 10, the number of sum of more than 10, divided by the number of everything, divided by the number of everything. Now, the sum of more than 10, the sum that gives us more than 10, what is that? What is that sum? More than 10. What is that sum? We can look for it from the table. You can see that when we add 4 and 6, it gives us 10, but we want more than 10. So it will be this one here. 5 and 6. 6 and 5 is also another one here. And then this 6 and 6. They'll give us more than 10. 6 and 3 is 9. It's not more than 10. 6 and 4 is 10. So 3 items gives us the more than 10. And then we also have the number of everything that we already know to be 36. So now we can finally solve our problem, that the probability that the sum is more than 10 is equal to the number of the sum of more than 10 divided by the number of everything. Number of everything. Now, the numerator is going to give us 3, and then the denominator is going to give us 36, and we're going to have 3 over 36. 3 goes into itself 1, goes to 36, 12. So our final answer is 1 over 12. I hope this helps. If you are still having little clarity problems with this video or this questions that we have solved, I will try and entreat you. Please take a little break. Grab a cup of water, take a little walk somewhere, come back more refreshed, and then you can go into the video again. You see that everything will come out very clear. If you haven't yet subscribed to our channel, please do us a favor by subscribing so we can be doing more videos to help as many people as possible. But before I come to you another time, please take care of yourself and take care. Bye.